So we're going to have to know a few things in this unit, especially about solubility, because it's going to be vital in figuring out if we can make these things called solutions. So if we have a soluble substance, then we can make our solution, but it depends. So solubility is the ability for a given substance, which we're going to call a solute, to dissolve in a solvent. So lots and lots of words that start with S, which is going to be fun. I know you're all excited to see 4 S words that all sound similar. So the solute is the substance you're trying to dissolve. It's the thing that you're trying to get rid of, or you're trying to put into something else to make some solution. The solvent is the substance that dissolves the solute. This is usually a liquid, and in our class, we're mostly using water. That's not saying it has to be a liquid. It can be a solid and it can be a gas. So that might be something we want to write down, is that these solutes can be solids or gases. So they can be solids, they can be gases. Aren't requirements for it to be a liquid. And even if it's a liquid, it doesn't have to be. Usually it's water, just because water is what we mostly make our solutions out of. But sometimes we'll use hydrochloric acid, which is a different liquid. We'll use other liquids. It just depends on what you're trying to make. So that liquid is not specific. It's just the solvent is going to be the substance you have a lot more of. You're not going to take a lot of a solute and try and put it in a small amount of solvent. You're going to have a lot more solvent than you will have your solute. So a lot more. And this is going to be a small amount. So you're going to have a lot more solvent than you will your solute. So there's going to be 2 types of solubility. There's one solubility that we're not going to focus on in this class a whole lot, but it's that likes dissolve likes, and that's going to be for our covalent bonds. So for covalent, like dissolves like. And so when I say like dissolves like, that's specifically about polarity and the fact that nonpolar molecules will dissolve other nonpolar molecules. Polar molecules are going to dissolve polar molecules, but we're not going to really see a whole lot of nonpolar molecules dissolving polar molecules. It's not going to happen as easily, which is why we can say that like dissolves like for covalent compounds. This has nothing to do with our ionic compounds, because we're going to be putting a bunch of ionic compounds in water, especially, and water is always a covalent bond, which means that this does not apply to our ionic bonds. So that doesn't apply to our ionic bonds when we talk about like dissolving like. That's just when we're talking about our polarity. For ionic bonds, that's going to be down here. That's going to be ionic bonds dissolving in a liquid, usually a covalent molecule. So when ionic bonds, when we're determining that solubility of those ionic bonds, you need to look at the ions for each of the elements or polyatomic atom or ions that are going to be combined. So we're looking at the elements or the ions or the polyatomic ions that we're using in that solution or in that solute. So that's our solute, is going to be that ionic compound. And when we're looking at that ionic compound, the ions that are going to be created, these are going to either be scattered throughout our solvent, or the ions are going to stay together. So if they're scattered around the solvent, that means it's going to be soluble or it's dissolved into our solvent. If the solute stays together, if it doesn't, then that means the ions don't break apart. They're not going to dissolve into the solid. So before we get on our solubility chart to actually determine this, let's draw out what we're talking about. We're going to draw out sodium chloride, and we're going to talk about either dissolving or not dissolving, or being insoluble or soluble in water. So if we have a container, a beaker, and I have sodium chloride, so NaCl, that's my table salt. If I'm putting that into a beaker of water, so I have my sodium with my positive charges and my chlorine with my minus charges, and there's a bunch of them in there. There's not just one of each. So if they stay together, they're insoluble. That means they've stayed together, and we're just going to have some water molecules floating around on the inside. And our water molecules are polar molecules, which means that they do have partial charges. The hydrogens are going to have partial positives, and the oxygen, which is more electronegative, has that partial negative charge. But if they're soluble, what's going to happen is we are going to see that in those water molecules, so we're going to see a bunch of water molecules, and then our ions are going to separate. They're not going to be near each other anymore. We're going to see some sodiums by themselves, a chlorine by itself. And if we had those three, we're going to see sodiums are all alone. Our chlorines are going to be off by themselves as well. So we're going to see our sodiums and our chlorines over in different places. They're going to be separated. They're spreading apart. They're dissolving into our solution. They're dissolving into that water, which would make it soluble. Are there any questions on what that difference means between soluble and insoluble? All right. So when we're determining our solubility, we are going to look at our solubility chart. We're going to use this solubility chart to determine if it's soluble or insoluble. It's going to be pretty simple once you look at the chart to determine this. You just have to remember to do it. So we have sodium chloride. So we're going to find sodium, which is right here up at the top. And we're going to find chloride, which is over here. And we're just going to draw our line until we meet up with one another. And we're going to read that it is soluble, which means what happens to my sodium chloride when it goes into water?
It split up.
It splits up. The ions spread apart and it dissolves. So it's soluble. Oh, man. That does not look right. That's right. So it's soluble in water. So this one is all about in water. But in most cases, our sodium chloride will dissolve. It is soluble in many things. All right, and then we have copper 2 chloride. So let's go to our solubility chart. Let's find copper 2 chloride. Is copper 2 chloride soluble or insoluble?
Soluble.
It is soluble again. We can find it right here as soluble, which we can put right here. Are there any questions on this solubility stuff? All right, then before we continue on to molar mass, I do want to talk about this wonderful stuff up here with our drawings. And I want to talk about those intermolecular forces that you guys should have watched that video about yesterday. So we have intermolecular forces, and I'm just going to write them over here. Intermolecular forces, IMF, for intermolecular forces. And if we're talking about water, H2O, can anybody tell me what intermolecular forces they think are there with just the compound water? We have a bunch of water molecules. Does anybody remember any of those intermolecular?
Hydrogen bonding.
Which one?
Hydrogen bonding.
Hydrogen bonding, perfect. Any other ones? All right, so the first one that I would always come up with, what were you saying, Raul?
London dispersion forces.
Exactly, London dispersion forces. So that was the one I was going to suggest first. Because all compounds are going to have London dispersion forces. That's just the force that holds them together. So it's between two compounds. It's not that bond itself. So if we're looking at water, HO8, it's not this bond, it's not that bond, but it's going to be that imaginary bond that we have between our two compounds. So this imaginary bond right here that holds the two compounds together. That's why we can have multiple water molecules in a glass when we're drinking it or in an ice cube. That's why multiple are present, because there are those imaginary forces holding it together. So they're not full bonds, but they're getting pretty close. And then the other thing I do want to point out is that hydrogen bonding is just a special dipole-dipole interaction. So a dipole-dipole intermolecular force. And do you guys remember what a dipole meant?
When an element is, or when a bond is slightly more positive or more negative towards one side.
Exactly. So our electronegativity isn't equal. We have a polar molecule, which means there's a larger pull to one atom versus the other. So we create partial positive and partial negative charges. Due to a difference in electronegativity. So our dipole is that creation of those partial positive and partial negative charges due to that difference in electronegativity. And hydrogen bonding is just a special dipole-dipole interaction, because hydrogen bonding only happens with the most electronegative elements. It only happens with oxygen and hydrogen bonded together, nitrogen and hydrogen bonded together, and fluorine and hydrogen bonded together. The only 3 times you'll see a hydrogen bonding. If we're talking about sodium chloride, NaCl, what intermolecular forces do we have there? What forces keep sodiums and chlorines near each other to make that table salt? Anybody have a guess? It's similar to, it's the same as one of the intermolecular forces in water.
London dispersion forces.
The London dispersion forces. So London. All right, so that London dispersion force is also in sodium chloride. It's in all of our elements, or sorry, all of our compounds. We're going to see that London dispersion force. But for sodium chloride, that's the only one present when we just have that sodium chloride by itself. Once we make the solution, or we put the solute, the sodium chloride, into the solvent, the water, once we make the solution, which is the sodium chloride in water, we're actually going to have a new intermolecular force come into play. Because it's soluble, we can see that the sodium, the positive ion, is near our oxygen, and the chlorines should be near our hydrogen. That's going to be because when we make water, we have the partial positive over here by the hydrogens, and the partial negative is over here by our oxygen. So we're creating that dipole, which means it's separating the charge just a little bit. Why the sodium and the chlorine are going to break apart, because they want to be near the other positive and negative charges, and they're not held together very strongly. We're creating this third intermolecular force that's going to be a part of this solution, and that's going to be ion dipole. And that's because we have an ion, the sodium, or an ion, the chlorine, next to a dipole, or a partially charged part of our polar covalent molecule. Are there any questions on the intermolecular forces? I know that was a very quick recap of things you should have gotten yesterday. If you guys have questions about it, please let me know. We do have one more thing I want to go over as a group before I'm going to let you guys go on working, and that is molar mass. And I'm going to tell you guys, you probably actually have seen this before because we've all done it way back in Unit 1. We just called it something different. So molar mass is the mass of 1 mole of a substance, and it's equal to the substance's molecular weight, or their average atomic mass. So molecular weight is just a fancy way of saying our average atomic mass. So now we're just changing the units that we use to talk about average atomic mass. We use AMUs before, or atomic mass units. We're changing that to say grams per mole. So we're just changing how we wrote the units. Everything else is going to stay the same. In order to understand what the molar mass means, we first need to understand what a mole is. And a mole is going to be probably the most important thing we talk about in chemistry class, and probably something that's going to stick in your head forever. And the mole is actually just a unit of convenience. It's like a made up unit, and it's made up to represent that there are 6.022 times 10 to the 23rd atoms or particles or molecules equals 1 mole. So 1 mole is just a fancy way of saying just a ton of atoms. So we have a specific amount of atoms, 6.022 times 10 to the 23rd atoms is equal to 1 mole. So we've just simplified how we're saying these atoms, the number of atoms. This is a specific amount that everybody knows. It's called Avogadro's number. And that's what we're representing as 1 mole, just a ton of atoms. And so when we're looking at the molar mass, we use that average atomic mass for each element. So we have 3 right here. We have sodium, we have chlorine, and we have copper. This time, instead of for average atomic mass, I know we rounded it usually. This time we are not rounding it. We're just taking it off our periodic table. So if we go to our periodic table and find sodium, what is the average atomic mass or the molar mass of sodium?
22.990.
Perfect. And that's the mass or the number of grams that equals 1 mole. Should be putting units. Grams of sodium is equal to 1 mole of sodium. So the abbreviation for mole is MOL. I know they made it real simple for you. And then putting on the units of sodium on the end, because remember, this is atoms of sodium we're talking about. The molar mass of chlorine will be a different number. So we need to make sure that we're specific when we're talking about each mass and the number of moles. Who could tell me the molar mass of chlorine then?
Wait, for chlorine?
For chlorine, yep.
35.45.
35.45. Perfect. That's the number of grams for 1 mole of chlorine. What about copper?
63.546.
Perfect. Grams of chlorine equals 1 mole of chlorine, and 63.546 grams of copper equals 1 mole of copper. Are there any questions on how we got those numbers? All right, let me just have one more thing to practice before you guys do some practice on your own, and that is going to be down here. So it says if you have multiple elements, so a compound, you need to find the molar mass of each and then add those elements together. So we actually just found all of those molar masses. So let's look at sodium chloride first. We need to find the molar mass of sodium, and we need to find the molar mass of chlorine, and then we're going to add them together. So we know the molar mass of sodium is 22.99. And we know the molar mass of chlorine is 35.45. We're going to take those two numbers and we are going to add them together. When we add those two numbers together, what do we get?
58.44.
And so that's going to be the mass or the grams of sodium chloride that equals 1 mole of sodium chloride. A shorter way of writing that is also going to be 58.44 grams per mole of sodium chloride, if you want to shorten your units. I want you guys to try and do the next one. So come up with your next answer. Take about 3 minutes to do so. All right. Did anybody come up with a value for the molar mass of copper 2 chloride?
98.996 grams per mole.
Does everybody agree?
Yes.
Yes, yes, yes. All right. I tricked you guys because we didn't do one thing. So if we look at this one, we have copper, we have chlorine, which I love that you guys found those. You had 63.546 and you had 35.45. But because sodium chloride, we have one sodium and one chlorine to make that atom. We just added them together. I tricked you because this time I gave you 2 chlorines and only 1 copper. So if we're finding the molar mass of the copper 2 chloride, we actually have to multiply this one by 2 because we have 2 chlorines in this compound. So we're going to multiply that one by 2 and we're going to get 70.9. And then we can add those 2 together. So instead of 98.996, you should get 134.446. Because there's 2 chlorines present. Do you guys have any questions on that one? All right. So then the last thing you guys have is practice with solubility and molar mass. And so if you look, there are 20 problems here. And I think that's a lot, and that's not actually